Okay, here is our overall sensor. This is our NXT input with the accelerometer, which outputs a voltage through these wires to our circuit. And just like as we stated before, it's used here for our comparators to compare against. And when they get activated, that gets sent up to the 741, which boosts the voltage, and then the transistor boosts the current so that that output can then come to this laser, which is communicating with that light sensor. And so this is wireless technology right here.
There are no wires between these two.
Yeah. And then this is connected to our lab jack. So here's our light sensor plugged in with the output of the light sensor going to our analog output.
Input.
And okay, the output.
It's going into the input.
Okay, well the output's going into the input of the computer. Whatever. And that is showing up here. And so what we basically use is the greater than comparator to basically turn this into a boolean, which we can convert into either a 0 or 1. So now we have our light sensor outputting either 0 or 1 for if the laser is on or off.
If you go up a little, here's where we put those into the arrays, and then they do things.
Okay, so this is all code so far.
I think it's obvious what it does. There's no explanation needed.
Okay, this part right here is just a timekeeping part where it just basically calculates the current time. And this is the input from our light sensor. And what this basically does is it takes it into an array to plot it on our graph to show when hits and misses are.
And I like this thing. Here's where we calculate the frequency. So because we have our code set up as basically ones and zeros for a hit or not, we can just sum them all up to get the total number of hits, and then divide by the time, which goes back there. So the hits divided by the time is equal to the total frequency. But that gives us that's like the overall total for the entire time that it's been running, which doesn't help us in some cases because, you know, if it's been running for a while and there's like an earthquake right now, it might still say like 0.5 or something, which is like, you know, not really accurate. So we also have a kind of recent frequency little thing, which gives you a little window of in the past 3 seconds what the frequency has been. And we did that by making the total array into a little subarray of the most recent things, and then doing the same thing of dividing the number of hits by the time, but only for that section. Okay, so if you look up here, we've got the code that can turn our buzzer on and off, which the control statement is the checking if the recent frequency is greater than 4. And if that is true, then the LabJack Easy Analog output will output 5 volts. But if it is false, it outputs 0 volts, so nothing happens and the buzzer does not go off.
And that's using a case structure.
But yeah, he can see it's a case structure.
Well, now he can.
I think he knows what a case structure is.
And here is the whole code, which exports it into basically just a file on the desktop. And you can use this to do all sorts of fun math.
And that it only activates this when it is finished with the loop, which only happens when you press the stop button, which is right here. The stop button stops the loop, and that is right down there.
So now we're going to show the code running with Austin shaking the input. And here the graph of the hits and misses along with total average frequency and our window for recent frequency. So take it. And you can see recent frequency is about 3 hertz that Austin is shaking it. and total is about 2 hertz, but that's not as helpful because
If I stop.
yeah, if Austin stops, it goes down to 0 immediately,
But the
whereas the
stays
total is counting down very slow. Now shake again. Faster. And going up to 5, 6, 7. Wait, isn't the buzzer supposed to go off?
Do we have it plugged in?
Yeah? Okay, so here's our code running. Oh. Hey, it works.
Yeah, it does work.
Okay, so if the reset frequency goes above 4 hertz, the buzzer goes off. Austin, shake it. And there it's on.
Kind of annoying.
It's supposed to be annoying. And as you can see, when our code is running, it's keeping actual seconds. Well, I mean, pretty close to actual seconds. And then if we click all the stop button, that's when it asks us to save all data. So we save it.
We save it.
We save it, and it shows up as a text file, which we can open with Excel.
We can open with Excel.
Yeah. And there's our data. And then if we plot it, you can see our data points in our waveform. So Austin, if a California taxpayer walks up to you and says, "How have you been spending my money?" You'll say,
What?
Say the thing.
This circuit could save lives, because you could just be sitting in a room one day and not know what's going on, and then suddenly this buzzer goes off, and you know that when that goes off, there's an earthquake, and you need to just run for your life.
Yeah. So Austin, what did we learn?
We learned that the lab room is haunted by a ghost.
What else did we learn?
Alright, don't look at me, look at the code. We also learned how to code LabVIEW, and this might look kind of confusing, but we actually know what's going on in this. So that kind of tells you something. Look at all these wires going places and doing things. We know what those do. There's like stuff going on right here with the booleans, and then up here is like the arrays with the shift registers. And then here, this is timekeeping. I thought this part was pretty cool, to get it in real time. This thing takes the time and outputs it of what the time is in seconds at the beginning of the code, and then we keep on doing that and then subtract the original to get how much time has passed. So that gives us an accurate time in seconds for our x-axis. We've also got the little control statements up here, and we've got things going into graphs and little numerical indicators, and we even have it going out into a text file.